Good afternoon, everyone. I'm Hong Yu. I'm a first-year PhD student, and today I'm very excited to lead the discussion of this paper, hardware information flow tracking. The reason why I picked this paper because when I was scanning through the list of papers, I was like, I had no idea what this was. So it would be I thought it was interesting to look at to get a good overview of this topic. But I did regret because a lot of pages. So I think what the purpose of this presentation is twofold, as professors mentioned. I wanted to share something I've learned from this paper, and also I'd love you guys to help me answer some of the questions I have heard around the presentation. Thank you very much. So I think hardware IFT is very similar to, if not exactly the same as tracking information software until we translate, for example, this HDL code to a gate level schematic, right? So in this case, we have input signals A and B and the output signal sum. And if we translate this to an adder, we can have two inputs and the output is sum. So we can see very directly the information is propagating from A and B to the output. So what IFT does is tracking the information, how it is propagated through the system. And so here we have in a set of objects or memory storage objects, for example, the ports, the registers, memory blocks, and a set of processes, right? So how the values are distributed in the registers and arithmetic operations. But I think at the beginning of this, I was really having a crisis, really convincing myself why IFT is needed, because we have already had a lot of techniques on a hardware level, like Intel FTX, ARM, as well as security testing, and also just like the security bits we have on operating systems like Linux. So maybe you guys can tell me why IFT is important or different from existing methods. Well, it can buy me in addition to existing methods. Yeah.
Why is it needed? I think in the most general sense, we in our lives like have security for some non-members, like use strong passwords for websites and make sure that we're not letting information go to places that it shouldn't go. And I guess, yeah, the paper they talk about originally this was formed at like the OS level, so we are talking about files and we are talking about like human synthesizable information, but everything. The performance is kind of moving towards like discrete hardware, and it's so being able to translate these ideas of classifying and keeping information of its own special docs with its own special policy. I think it's like something to take care of, especially like as because we're getting closer to the hardware because the hardware is just a little bit more scale stuff.
Yeah, I think that's more than I was expecting, but yeah, very comprehensive. Yeah.
Okay. So yeah, the idea I had was that so all of these features here are features that have to be used correctly,
Yeah.
and features that you need to explicitly use. For example, the hardware security features have to be used correctly, and the access control also has to be used correctly.
Yeah.
So these are kind of like individual components that you add to your software to hopefully make it more secure. What I think why IFT is different from these individual components, that IFT is kind of like, it's not a component that you add, it's more like a component, no, it's not a component you add on the outside, it's kind of like something that goes from the bottom up, right? It looks like your whole system from the basics instead of adding like some checks at the top, It looks at the information that you have on your system from like a lower level. So actually like a way to highlight why this is different is that you can use IFT to like verify that you have your access control set up in operating system correctly, or you have the hardware or like the security features work as they should. So I feel like IFT is like on a much like deeper and more applicable level than these other ones that are maybe more like surface level.
I totally agree. It's very fundamental as to like what security means actually is.
Yeah, I just wanted to add on to that. I think IFT is unique compared to these or the existing features is because it's more of a model, more of a formalism that's universal to every single abstract layer.
Yeah.
And I think that's why it's unique.
Yeah.
Just one more for the IoT is very comprehensive. I know the paper it mentioned that it can be for kind of the time inside channels.
Yeah, exactly. Modeling timing side channels as well. So I think like my reason was I conjured up a very simple example to show why this could be useful and different from existing techniques. So for example, in my company, the CEO has access to some secret files, and I'm the janitor, having no access to those secret files, but we both have access to the trash can. What happens is that once the CEO disposed the files, I will have access to the files. Right? So the access control is about guarding the information, like access to the information, and the name applies. And the information flow tracking is about tracking how the information is propagated even after the information is being produced. So it's a very fundamental framework for modeling security, as many of them. So yeah, the formal model introduced in this paper, the first one was Danning's information flow model. And what this is, as we've talked about, we have XYZ, a set of storage objects, and the tags or the classes, security classes. And information flow analysis is the most commonly used method to reason about security. And this flow, this model consists of also an interesting operator, which is this combining all plus operator. It produces an operator by combining two of them, a class, sorry. So for example, I'm computing 5 minus 3, and I can just compute this least upper bound, as primum of the two, getting out of a label of the results also being high. And also the arrow means the label, the information can flow from one object to another. What's interesting is that in the paper they also described in length the greatest upper bound, that was a typo, greatest lower bound, the infimum operator. So basically if I'm calculating the whole dots between x and y, then that's all the objects that can flow to x, both x and y. But actually I don't know still where, because that was the only place in the paper they mentioned this, and I don't know where we can use this. Maybe any ideas where we could potentially use this operator? No, okay.
Sorry, question.
Yeah, please.
I still couldn't get what's the meaning of the less combining operator. Why is it called least outbound? What's the bound or the comparison between?
Yeah, that's a good question. I will have you to hold on this for a slide. I will introduce actually what does it mean to have a bond on it. Yes, here it is. So actually, the Danning's information model also introduces something called the security lattice. So the security lattice consists of a set of objects, classes, and a partial ordering between those classes, right? So this is what I meant by the upper bound and lower bound. In this case, we have the high label and low label, and in this case, the second figure shows that the trusted information can flow to the untrusted, but the untrusted sources can't tamper with the trusted, right? So this is the integrity, the property, and also we can formulate this in a similar way, saying that unclassified information can't flow to the secret sources, and this is the confidentiality. And these are so-called the linear lattice, because you have a linear relationship from the lower bound to the upper bound. We can also have something called a multi-layer, a multi-level security model, where you have the lower bound here and different labels A, B, and C, and you combine them to form, by doing operations, maybe two operands having operations, then after that, A and B would be the combined label of that result, and so on and so forth. So you can have this multi-level relationships. One thing is that the information can only flow from bottom to up. It's kind of counterintuitive, but you can only flow up, and for the labels that's not comparable to each other, we need to, there's no information flowing between them. So that's.
Can you just go back one slide?
Yeah.
So,
please.
no, I'm really glad you explained this pretty well. So, what's the value of having a formalism like this? So, this is like a mathematical formulation. You know, if we didn't have this, we could probably still argue about everything that we argued about or reasoned about. What's the value of something like this?
It's easier to communicate ideas.
Right, it's easy to communicate the idea, especially as you go from context to context, right? You may go from 4 different contexts, and in fact, even across different sub-communities, right? Because if you go across different sub-communities, each one may sort of reinvent the same kinds of concepts and start using slightly, different language, different words, different terminology, and especially in computer science and engineering, it's pretty vast. There are many domains. You work in networking, a lot of us work in hardware, and so on. Different communities will just reinvent things and may not even get it right first time, and then they'll go through these iterations. But if there's a formalism that we can learn about and share with different across communities, then everybody can sort of point to the same thing. Now, here's a formalism that can be used in networking, it can be used in software, it can be used in hardware, and essentially the same reasoning that one community, one domain has gone through, you can largely use in a different community and domain relatively quickly without needing to reinvent things.
Yeah.
Just explain one more time the integrity, like trust and error. Like, what exactly is that error indicating in this case? Trusted or untrusted?
Yeah. So the question is, what does this error really mean? Like pointing from trusted to untrusted. I will give a few examples of the integrity constraint. But basically, the untrusted would be, for example, a user input. The untrusted would be the user input. A trusted could be, say, a sensitive register. And the sensitive register could be giving information to the user input. But in terms of integrity, you can't really tamper that sensitive register, if that makes sense. So, yeah.
So it's like the trusted register can affect the untrusted register, but not.
Exactly. Yeah. One very important, interesting concept is this non-interference model. So it's a multi-level security model operating on all combinations of input and output. So it says that the low object can never learn anything about the high data, and it's defined over semantics. So meaning that we can't reason about non-interference just by eyeballing the structure of the HDL code or the gates, we need to reason about them, the behaviors of our circuits. And it's end-to-end, it's very slow. And yeah, later we'll show one of the methods is that using this security lattice as a type system, and we can reason about a security-based for enforced typing to reason about non-interference property. And I stole a slide from the professor. So basically, information can flow from the high level to high level, low to low. But if you want integrity and confidentiality, then the flow, you can't do this crossflow. So the paper also introduced a couple of challenges of this non-interference flow. So the first one is that you have various very different types of computations performed by different hardware models. And we have, in hardware design, we not only have time, but we also have space. Everything is working in parallel intrinsically. Right? So tracking all the different things happening at the same time is very difficult. And also, one thing they mentioned is that in hardware, there are just too many more objects compared to reason about software. I put a question mark here because I'm not sure. Because in software, we can have unbounded number of objects, as Professor mentioned in the start of this semester. So I'm not sure if this actually is a challenge. What do you think? Well, we do have a lot of gates, right? But they are still bounded finite. So another is, I was thinking maybe this property is too restrictive in practice. So do you agree with this statement? Like do you think like non-interference is actually practical in most cases? Do we do it like on day-to-day lives without modifying this definition of like, high to high, low to low, no interference?
Actually, I'm going to go back to 3. So I had a question mark also when I was reading it. So I think again, I'm not sure. I don't know what the authors were thinking. But connected to point 2 is hardware things can have many compute orders. So if there's concurrency, things can go on in parallel. You can have many different interleavings.
Oh, I see.
So I'm not sure if that's where we are going with the comment 3 or not, but that's the one thing that came to my mind that I made a note to myself.
I see. Yeah. Just quickly summarize. One of the potential reasons is that maybe because of the parallelism, for the same number of objects, you have a lot more combinations potentially happening in the ordering, which makes the flow analysis a lot harder. Yes.
I think in comment number 4, I think you touched on a good point. It's like, it could be potentially too restrictive if we immediately jump into some security protocol design. But I think by iterating through different levels of restriction, we can get to something that's much more appropriate. And also, I think in the paper mentioned that if it's too restrictive, then it can have problems with time complexity. Like if it might not be able to just finish running.
Yeah, that is true. Yeah, the complexity here is definitely a concern, and we can directly boil on the protocol to something private. But what I was having in mind was that in hardware we like there's a lot of shared components, right? We have shared cache lines among processors, and you have inter-process communication as well. So if you don't allow those communication or shared buses interconnect, if every component has their dedicated path, no interaction, I felt this is not something practical. And also, if you can recall, Professor also mentioned like something called a predicate on the object. So it's conditions where you can actually downgrade or declassify some objects upon conditions. For example, like the bidding, like the bids are released after the bidding process. But what's interesting is that in the paper they didn't mention anything about the predicates or downgrading declassification policies. One nitpick from me. So there are a set of security policies, properties mentioned, described in the paper. So a property or a security policy is basically a constraint or rule we impose on this hardware design. And in IFT properties, is so-called hyperproperties that we've seen just a moment ago. So we need multiple execution traces, right, to determine those properties. Some example properties, firstly, confidentiality. So the secret information can't be propagated to the unclassified sources. So, for example, we have some hardware resource arbiter here. The request, so some sensitive request. Sorry, I am using the system Verilog assertions to demonstrate where we assume that the assume basically labels that object, right? We label a sensitive request to be high, and then we assert at the end of the execution to see if any acknowledgement exposed to the public to be high. So we don't want any sensitive requests sent to the arbiter to be influencing any other unclassified acknowledgement. Similarly, we can express this integrity property where we assume the user input to be high, and then for a given processor, we want to test if the PC or the program counter is being tampered by checking the class afterwards.
So basically, so this is really checking the label. It's not checking the value. So the high and low here are referring to labels.
Yeah.
Whether it's a high security level or a low security level. So it's referring to the labels, not the value of that signal.
Exactly. Yeah.
So it's a label. So it's basically saying the user input there has a high label. So essentially, this is sort of assertions on tapes, and that's the reason why you can get away with a single trace property. So you're actually getting away with a single trace property here because you're using, you're reasoning about tapes or labels. So this is actually not doing self-composition, not doing hyperproperty.
Yeah. Yes.
So basically, these highs and lows are the security level labels. And this is security level high and that security level low. This is not the value of that signal. It's not saying request I, the signal is high. It's saying the level of request high is high.
Yeah, thanks very much for pointing it out. So I'm using some synthetic sugar to assert. So the assertion here are checking the taints, not the.
So the taint and the label are sort of used interchangeably, right? So if you say high level, then you're basically saying this is tainted.
Yeah, so this is basically after the taint analysis has done over the traces, and this is we are checking the results. Yeah.
How is assume different from assert?
Yeah, so the question is, how is assume different from assert? Intuitively, I think assume is the constraint on the inputs. So if we don't have assume, then this would be random testing. So you are just having all possible kind of scenarios, and you check the output assert. Assume is basically having an assumption as like what the input could be. So it's an additional rule on the inputs. If that, The rules can also be the properties can also be a double bridge where you check. In this case, memory isolation, one location, the request from one location is not affecting the other location, and so on and so forth. what's interesting is that they also mentioned this timing side channel, as previously mentioned, by asserting using specific syntax. Here, like for a cipher, we are checking, so given the key, we're tinting the key, and we are tinting the p-tags. But what we are getting out of, we are not checking the c-tags, the results of c-tags, but actually we are checking the whole process if this is a constant time execution or not. If it's not, when producing c-tags, we will be having a label on top of as a high label.
So basically, the way you should read the ciphertext equal time. So think of that as the done signal or the valid signal at the output of ciphertext. So actually, this bears just 1 more minute. So we'll see this. So actually, we will actually do a demo with Jasper Board. So Chinhan, who's my PhD student who's worked with some real architectures, he will do a demo the next one of the lectures. So one of the things that we found out was that if you're checking timing side channels, essentially the constant is that there'll always be some signal in the design that's proxy signal for the timing. By proxy signal meaning that if you observe that signal, you will get to know whether there's a timing side channel or not. And that proxy signal is basically some kind of a done, valid, done/valid kind of a signal at the output of a module whose completion is time independent. Even in a processor, when you have an instruction commit, so if you're looking at to see, is a sequence of instructions potentially leaking timing, you're looking at the instruction commit sign, basically the commit signal, because there's a commit signal which is telling you when the instruction is finally committed. So if you're tracking the commit signal, then if there is a timing dependence for a sequence of instructions, when that commit signal for some instruction goes high, will be different. So your commit signal is a proxy for timing. Okay, so instruction commit, for example. So these are all, proxy for timing. And basically here, whenever you see something like this, the way to think about it is, what's your proxy signal for timing that will tell you when your computation is done? There'll be some kind of a done or a valid or a commit signal coming out of that module. So that's basically what this ciphertext equal to sub time is doing. So it's sort of a notation that's saying that there'll be something that will tell you when this is done.
Yeah, to quickly summarize, so for a dedicated IP, for example, we're checking the done signal, the finish signal for that IP to check the timing property. And there are different types of information flow. So I will just give, and what's interesting is that in the paper, they are categorized into 2 types of information flow. One is the physical flow, where we have the execution time, power, electromagnetic radiation, and so on and so forth. And the second category is the functional flow, and was the focus of this survey. So for example, we have the implicit flow or context-dependent flow, where we look at this HDL code to determine whether the select signal, the information from the select signal is propagated to the output or not. We need the context to determine. And also we have explicit flow, which is so-called the data flow, where we can just look at the schematic and to see, okay, because the information is propagating towards the output, there is definitely information flow between the 2 objects. And B is at the gate level. A is at the RTL level, and C is at the gate level. What's interesting to me was that they are representing exactly the same thing. But A is at the algorithmic or semantic abstraction level of abstraction. B and C are like a much lower level of abstractions. And by lowering the level of abstraction, we can actually turn the same thing from an explicit flow into an implicit flow to explicit flow. So the level of abstraction really matters here.
So, okay, hold on. So your final point is absolutely right. Level of abstraction matters, but I'll just add two more things. So actually, B is also implicit, because in B also the flow is going from not directly from select to multiplexer, but indirectly through A and B. So B is just a circuit diagram version of A. So A and B are both implicit.
Oh, I see.
C is explicit because the value of select directly flows through the gates.
I see, right.
But as you point out, the main point is that the level of abstraction matters. But what this also says is, this whole implicit versus explicit dichotomy is a little fuzzy. It's so it's not particularly meaningful. It may be helpful at a high level just to think about what's actually causing it. But finally, it's information flow, one way or the other. So the reason, actually, we didn't spend enough time here. So the reason why either here or here select is indirect or implicit is because the value of select is not what shows up at the multiplexer output. Whatever shows up there is either A or B, but by observing which of these two flows, you can guess what select, or not guess, you can determine what select will be. So in that sense, it's not explicit, it's implicit. Whereas in that gate level circuit, you don't have this high level information. So technically, the value of select through some logical equations is getting to the output there.
Yeah, thanks very much for pointing it out. So so for the selector, the selecting signal is still kind of implicit because unlike A and B, it's not directly related to max, like flowing into max. Actually, I do share with your perspective, in terms of whether this kind of separation is useful or not. I will talk about that on the next slide, but for the physical flow here, we have this quintessential example of cache access and DRAM access depending on this condition. So basically, it's saying that this is by having a selecting different routes, you can actually have different timing perspective. This is leaking the information to the valid signal implicitly. Yeah, I was thinking, well, if we have already the category of implicit and explicit, then there's no need to separate the physical flow, right? We can just call it the implicit flow already. And also, I was thinking, they were saying, by lowering the abstraction, it's getting harder and harder to say which flow is implicit and which flow is explicit. And I was thinking, well, why do we need such a distinction in the first place, right? Or, well, maybe it's useful, I don't know. And also, why don't we just lower all the abstraction to the lowest level, to the gate level, and to make the flow explicit? I think maybe the second one is more obvious, but the first one is still kind of perplexing.
Yeah, I mean, for the second question, it's just generally the same reason that anything has abstraction, just because if we try to take a complex design and always break it into a abstraction, and the complexity would explode.
By complexity, I guess it's kind of the computation.
Yeah.
Yeah.
I think it's useful, if you're making a comprehensive model that's like an IFT, it is useful to distinguish between control and data, or the select that would be the control information flow, and that's a really simple distinction. And I think that's really all that this is useful for.
Yeah.
Because I would have the same observation. This is all just gate level, explicit flow, but it makes sense to add just extra information to this IFT.
Yeah. I totally agree. I think in the paper they mentioned that certain policies are defined specifically for explicit flows and implicit flows. I think having that distinction in actual information is useful. And for the second point, as we will see, when we are lowering the level of abstraction, yes, it makes the reasoning of flow, like information flow, easier because we don't have the syntax and whatnot. But yeah, if we have like explode the design a cell into like different components, then it can really increase the complexity, the computation. So yeah. Exactly. So I think the distinction really makes a difference, like in terms of semantics and helping the development debugging process. And so different level of abstractions introduced in this paper. So they have this whole catalog of different the hierarchy. So at the top, for example, we have the system level of overview. We have some like dynamic IFT, where you can conduct, you can have a hardware coprocessor processing dedicated to the tint analysis logic alongside the actual operations, with shadow memory tracking like which part of which block of data is moved to where and so on. And the algorithmic level of abstraction, you can have like IFT enhanced HLS that automatically generate some hardware to support this logic, flow tracking logic, and also we can have do IFT at the ISA level, having instructions associated. Instead of a single instruction, we have a tuple with capability vectors attached. Similarly, we could have security typed HTML language at the RTL level, for example, sec Verilog and sec Teasel. And at the gate level, there's very established glyph work, and you can do some beautiful math in a very unified way to reason about both implicit and explicit flow. They also mentioned something at the circuit level. No idea what this, how this works, but they say, you know, we can reason about over continuous signals, which is interesting. What they, I think, didn't mention is another flow, another work. This paper was published in 2021. This survey, this paper was what came after that. So they also, this work, I think Cell Lift introduced another like in between abstraction of RTL and cell level. They introduced some macro cell and showed that actually we can leverage some semantic tricks to reason about all types of combinations much easier, much more scalable compared to reason about the same property at the gate level. Feel free to check it out after that. So at a very high level, what we've discussed is that we have relatively low overhead, but we have complex syntax to reason about implicit and explicit flows. But we are lacking the amount of detail we need in terms of hardware, so the designers need to make conservative assumptions and having a coarse-grained view of the system. But as we are going down the hierarchy, we have a lot more information about the hardware design itself, and by the merit of cycle-accurate information, we can reason about the timing very accurately, and we can model all the flows implicit because the logic is sort of flattened, right? And we can model like side channels using logic, which is fascinating. But it doesn't really scale to larger designs, and I think what this survey also presents is kind of how these work, different levels of abstraction are navigating through this hierarchy of complexity by trading off preciseness and performance. With our yeah. So yeah, last time we talked about the different abstractions, or different levels of abstractions. of information flow tracking and how they basically are navigating this trade-off space of like preciseness and complexity. But what I didn't introduce is the definition of preciseness. So in this paper, they have I would say, a very peculiar definition of preciseness. Last time we talked about how we model information propagates. So the IFT can be modeled as a function taking n inputs, I1 to In, and produce an output and saying that this output class is what. And preciseness is defined as if we have like the output is only labeled with the output label is only changed if one of the input has changed. So if one of the inputs can influence the output, then there is information flow, right, from the input K, for example, to the output label. So that's preciseness. So what I mean by that is if there isn't any like correlation or change propagating from the inputs to the outputs, then there is no information flowing. So by this definition, how they defined imprecise IFT is where you only take into account the input labels when we are kind of computing what the output label is, what output label class is for O. So in this case, if you can recall, the O plus operator is the combining operator, so it's the supremum calculating the least upper bound over all the labels we've had here. And for this imprecise algorithm, it's relatively cheap, so the time complexity is equal to the power of n. It's exponential because we each and every single of the label can individually influence the label of the output. So we have 2 to the power of n combinations. Okay.
Could you just elaborate on the last part about time complexity? Why is exponential? I just don't quite see it.
Yeah. So the question is why the complexity is exponential with this question. I'm allowed to ask questions. Yeah. Any ideas? So what's A? Yeah, so the capital N here is the number of inputs. So here we are considering only the class of each input. That's why, the capital N is the number of inputs.
I guess because for like a given output made up of some combination of inputs, and in the end determines the number of possible combinations of inputs.
Yeah, exactly. So I stumbled on this as well because I was thinking, well, every time you just individually add a label to it and you check whether there's any information flow or not. But it's like, so the way I convinced myself of this complexity is I was thinking of this as checking entailment. Right? So every time you want to check if, say, one of the, well, in this case, we are checking label A is entailed by some combination of other labels, then we need to do this combinatorial check, right? So every time we need to check, get rid of one label and add another. So it's not sufficient to just serially check every one after.
And then these labels are zeros and ones, depends on whether security is like 0.
In this case, I think it's only high and low. I also found some other problems because I felt that this analysis was even simpler than what we discussed in the lecture, like the static analysis, right? Because we are not taking into account even the structure of the context of all. So the static analysis or imprecise analysis here is taking into account only the labels. So that's why I thought it was kind of a very crude categorization of preciseness and impreciseness. So preciseness in their definition is taking into account the actual input. So in our case, I think we've discussed checking whether the inputs, like the range, we will never will ever reach a certain branch. And the time complexity here is also a bit hard to gain. So it's too powerful.
So this sort of you can understand from if you leave the first, then you're saying that the n inputs have to be n possibilities, and then for each of those possibilities, you essentially have to do one of the previous steps.
Yeah. All right. Yes. So some I find what's helpful is looking at their examples. So they give a N2 gate and an example of an imprecise information flow tracking here is that's regardless of what this circuit is actually doing, as long as there is a high input, we take the least upper bound of both of them, and we say we label the output as high, so it's imprecise. But if we look at actually what AND gate is doing, then A will kind of falsify all the outputs although one of the input is open. So this is what we mean by preciseness. What I found still confusing was this example. So this lattice they give as an example here. So what they wanted to show here, so the AT, so A kind of small case t, this means the label of an input, right? AT, BT, and the cancel out means the don't care value of that. So what they wanted to show here is that the most fine-grained analysis at the top, and gradually we can cancel out, we can kind of disregard the inputs one by one to make it more coarse-grained, and then finally at the bottom is the most coarse-grained analysis, I guess. And then they introduced a lot of verification techniques. For example, they made the very clear distinction what they mean by static, what they mean by dynamic. But Professor last time we talked about like the definition here in hardware is very different from the software context. And simulation-based verification as well. So they are checking using simulation the reachability of the undesired states. So we can check if the image can be part of the undesired states. And also formal verification techniques as well. I won't delve into the details. As well as emulation, I think we can do simulation. Instead of doing simulation, we can actually implement prototype staying on FPGA or even doing virtual prototyping, which is kind of one paragraph introduction. So I think they mentioned a few future directions. The first one I find is very interesting and is something I think I would love to do a project related to this. So I think for what most prior works were focusing on is doing this information flow checking, so the actual checking of violations. But building the formal methods or the constraint model itself is sometimes not a straightforward thing to do, right? Because you need expertise to specify what constraints correspond to that security property. So I think there was interesting work from S&P 2020, automatically mining or kind of defining, translating one set of specifications to another hardware setting. So just to ease a bit the the amount of effort you need to specify the constraint model. And also they mentioned the parameterized security properties, the IP, and access, providing a hardware access control policy language. Automated debugging, finding the security information bridge is one thing. Actually, root causing that bridge is equally hard as well. And also, they touch upon the possibility of extending existing works to AMS circuits and other potential research directions.
So yeah, some of these things we'll see a little bit later. So unfortunately, when you sort of are doing the paper-based presentations, the papers don't need to follow a build-up sequence of things. So that's partly what I'm trying to do in the lecture, so that we build up things. But there'll be some references here. For example, the point 5, which is looking at information flow tracking techniques to analog attacks and so on, which we'll be looking at later in the course. So we'll come back to this point when we do that.
And I think that's pretty much what I wanted to talk about. If you have to remember anything from this presentation or paper, I think two very important messages. IFT is very useful not only in the software context, but also increasingly being used in the hardware context as well. And different abstractions and methods are navigating the trade-off space. The potential missing pieces we've discussed, like the classification methods, downgrading methods, like different level of abstractions, as well as the preciseness definition, and potentially combining IFT with other techniques. I think that's all I have. Thanks.